Okay, imagine you're way up high, maybe in a hot air balloon, just drifting. You're completely surrounded by, well, air, the atmosphere.
Right, this huge envelope of gas. It's invisible, mostly,
Yeah.
but it dictates so much.
Totally. And that's what we're diving into today. It's not just floating, it's like the planet's life support.
And it's got this incredible history, how it formed, how it works.
Yeah.
It shapes everything, our weather, our climate, the air we actually breathe.
Exactly. And you listening, you sent in a really great chapter covering Earth's atmosphere and climate. So our mission today is to pull out the really key stuff.
Yeah, like how it all started, what it's made of now, those layers.
The forces driving weather, climate patterns. We want to hit those aha moments, Understand hurricanes without getting totally lost in the jargon.
Right. We'll basically walk through this chapter. Origins, the structure, how air moves globally, weather like cyclones, thunderstorms.
All the way to global climate itself.
The whole picture.
Okay, let's start at the very beginning then. The chapter talks about Earth's first atmosphere. What was that like? Very different, I imagine.
Oh, completely different and very short-lived. See, right after Earth formed, its gravity pulled in some of the super light gases from the solar nebula.
Like hydrogen and helium, the really light stuff.
Exactly. So for a little while, we had this thin atmosphere of just hydrogen and helium. But it wasn't built to last.
Why not? Too light to hold on to.
Pretty much. The early sun was way more active, blasting out intense solar winds. These winds, plus the fact that hydrogen and helium are so light, they just escaped.
Reached escape velocity.
Yep. They were just stripped away into space. A cosmic house cleaning, basically. Shows how chaotic things were back then.
Okay, so attempt number 1 failed.
Yeah.
What came next? The second atmosphere.
That one came from the Earth itself. As the planet cooled and differentiated core, mantle, crust-forming volcanoes started erupting like crazy.
Volcanic outgassing.
You got it. Gases trapped inside the Earth, dissolved in magma, just bubbled out. Think opening a giant soda bottle.
So what was in that volcanic breath? Still not like today's air.
Not even close. The big one was water vapor, H₂O, maybe 70, even 90% of the emissions.
Oh, steamy?
Very steamy. Plus tons of carbon dioxide, CO₂, and sulfur dioxide, and then smaller amounts of things like nitrogen, ammonia, maybe some methane too.
And comets maybe chipped in a bit too.
Yeah, the chapter mentions comets likely delivered some water and gases as well during impacts, so a mix from inside and outside.
Okay, so a hot, steamy, CO₂-heavy world sounds unpleasant. How did we get from that to something breathable?
The key was cooling. As the Earth's surface cooled down enough, all that water vapor in the atmosphere could finally condense.
Rain. Lots and lots of rain.
Exactly. Millennia of rain filling up the ocean basins.
Yeah.
That massively reduced the water vapor in the atmosphere, and those new oceans were crucial for dealing with the CO₂.
How so? Do they just soak it up?
Pretty much, yeah. CO₂ dissolves really well in water. It forms carbonate ions. And those carbonate ions could then react with calcium ions in the water from weathered rocks, and form solid carbonate minerals. Limestone, basically.
So the ocean started locking CO₂ away in rocks.
Exactly. Plus, CO₂ also reacts with silicate rocks during weathering, if water's present. So multiple ways the oceans and water cycle pulled CO₂ out of the air, planetary scale scrubbing.
That's amazing. And that helped stabilize the climate, stopping a runaway greenhouse effect.
Absolutely crucial. But here's the thing, it didn't remove all the CO₂, and that remaining bit was essential.
Why?
It acted as a greenhouse gas, trapping just enough heat to keep the early Earth from freezing solid once the sun was a bit less intense. If all the CO₂ had gone, or if it stayed too hot for oceans to form,
We could have ended up like Venus, scalding hot, thick CO₂ atmosphere.
precisely, a Venus nightmare averted, thanks to cooling in oceans. It's a fine balance.
So water vapor down, CO₂ mostly down. What gas started to dominate then?
Nitrogen,
Uh,
N2. Remember the ammonia from volcanoes? Well, ultraviolet light from the sun broke it apart.
Into nitrogen and hydrogen.
Yep. Hydrogen, being super light, mostly escaped to space. The nitrogen atoms paired up into stable N2 molecules. And nitrogen is pretty unreactive, so as other gases decreased, its proportion just grew.
Okay, so nitrogen builds up. But the real revolution was oxygen, right? Where did that come from?
That's the third atmosphere, the modern one. And it's all down to life. Specifically, cyanobacteria.
Blue-green algae, photosynthesis.
Exactly. Around maybe 2.4 billion years ago, these little guys figured out how to use sunlight, water, and CO₂ to make energy, and the waste product was oxygen.
A biological game changer. But it wasn't like flipping a switch, was it? Did oxygen levels jump right away?
Oh, not at all. It was incredibly slow. For maybe hundreds of millions of years, all that new oxygen just reacted with stuff.
Like iron in the oceans, forming those banded iron formations.
Exactly. It dissolved in water, reacted with iron, rusted rocks on land. These were oxygen sinks. They had to be filled up first.
Like mopping up spills before the bucket fills?
Good analogy. So even by 2.4 billion years ago, oxygen was maybe only 1% of today's level. Barely anything.
Wow. When did it finally get high enough to, matter for bigger life forms?
It was a long, slow climb through the Proterozoic, maybe a boost around 1.2 billion years ago with algae. But breathable levels, like maybe over 15–20%, probably not until around 600 million years ago.
And that timing lines up with the explosion of complex multicellular life, doesn't it?
It does indeed. More oxygen allows for more energetic metabolisms, larger bodies. It seems to have been a key enabler for the Cambrian explosion and everything that followed.
And oxygen had another huge impact up high, right? Ozone.
Absolutely critical. Once you have enough O2 molecules in the upper atmosphere, UV radiation can split them into single oxygen atoms.
Oh, the reactive atoms.
Right. And these single O atoms can then combine with regular O2 molecules to form O3 ozone.
And that ozone layer up in the stratosphere
Absorbs most of the really harmful UVC and UVB radiation from the sun. Without that shield, life on land would have been incredibly difficult, if not impossible. DNA gets fried by that stuff.
So the air we breathe, the shield protecting us, products of billions of years of geology and biology interacting. Mind-blowing.
It really is. And oxygen levels haven't even been static since then. The chapter mentions fluctuations.
Yeah, like peaking in the late Paleozoic.
That's right. Evidence like ancient charcoal suggests oxygen might have hit maybe 35% during the Carboniferous and Permian periods.
35%. What would that do? Giant bugs.
Well, it might have helped enable some of the giant insects we see fossils of from that time, yeah. Respiration is easier with more O2, but there's a big downside.
Fire.
Exactly. At levels much above 30–35%, stuff just becomes incredibly flammable. Wildfires would be constant, devastating. It's possible runaway fires could even cause oxygen levels to crash if they wiped out too much plant life.
Whoa.
Yeah.
Another delicate balance. Okay, so that's the atmosphere's epic origin story. Let's jump to today. What's the basic recipe for the air around us right now, assuming it's clean and dry?
Okay. Near the surface, dry, clean air is overwhelmingly nitrogen, about 78% N2,
Okay.
then about 21% oxygen, O2.
So that's 99% right there.
Pretty much. The last 1% is all the trace gases. Argon is the next biggest, almost 1%. Then tiny amounts of carbon dioxide, neon, methane, helium, hydrogen, ozone.
And some of those trace gases, even though they're tiny amounts, have huge effects, right? Like CO₂ and methane.
Absolutely. They're powerful greenhouse gases. Even in small concentrations, they trap heat and regulate the planet's temperature. Without them, Earth would be frozen.
And ozone, tiny amount overall, but vital up in the stratosphere for that UV protection.
Couldn't live without it.
The chapter also mentions aerosols. What are those exactly? Not just hairspray, I guess.
No. Atmospheric aerosols are just tiny solid particles or liquid droplets suspended in the air. Really, really small.
Like what kind of stuff?
Oh, all sorts. Sea salt from ocean spray, dust blown from deserts, volcanic ash, soot from fires, pollen, little droplets of sulfuric acid from volcanoes or pollution. A whole mix.
And they matter.
Oh, yeah. They affect visibility. They can reflect sunlight back to space, cooling things down or absorb it, warming things up. And crucially, they act as condensation nuclei.
Seeds for clouds.
Exactly. Water vapor needs something to condense onto to form cloud droplets. Aerosols provide those surfaces.
Got it. Okay. Heat and temperature, they're related, but not the same thing, are they?
Right. Important distinction. Heat is the total kinetic energy of all the molecules in something, how much they're all moving or vibrating combined. Temperature is the average kinetic energy of those molecules, how fast, on average, they're moving.
So a huge amount of lukewarm water has more total heat than a tiny bit of boiling water, even though the boiling water has a higher temperature.
Perfect example. Exactly that.
And where does the atmosphere get its heat from? Does the sun heat the air directly?
Mostly no. That's a common misconception. The sun's energy, mostly visible light, passes pretty much straight through the atmosphere.
So what does it heat?
It heats the Earth's surface, the land and the oceans. Then the warmed surface radiates heat back outwards, but has longer wavelength infrared radiation.
Ah, and that's what the greenhouse gases absorb.
Precisely. Gases like water vapor and CO₂ are really good at absorbing that outgoing infrared heat, trapping it in the lower atmosphere. So the atmosphere is mostly heated from below by the Earth.
Like a pot on a stove.
Kind of, yeah. Plus, there's significant heat released when water vapor condenses into clouds, that latent heat we talked about. Direct absorption of sunlight by the air itself is a smaller factor.
Okay, heated from below, that drives convection, right? Hot air rising.
Yes, and that ties into pressure and temperature relationships. Heat air, it expands, becomes less dense. Cool it, it contracts, becomes denser.
And that matters when air moves vertically. Adiabatic changes.
Hugely important. Adiabatic means changes in temperature happen without adding or removing heat from the outside. It happens just due to pressure changes.
How does that work?
Okay, imagine a parcel of air rising. As it goes up, the pressure around it decreases, so the parcel expands.
Right.
That act of expanding uses up some of the air parcel's internal energy. The molecules slow down, so the air cools. That's adiabatic cooling,
Just from expanding.
just from expanding into lower pressure. And the opposite happens when air sinks. It gets compressed by higher pressure. That compression adds energy, molecules speed up, and the air warms adiabatically.
Without needing a heater.
Exactly. And the rate is pretty predictable for dry air. It cools about 10 degrees Celsius for every kilometer it rises. Moist air cools a bit slower because condensation releases latent heat.
That seems fundamental for weather.
It absolutely is. Drives cloud formation, stability, everything.
Okay, speaking of moisture, humidity. What's relative humidity really telling us?
Relative humidity is a comparison. It's the amount of water vapor currently in the air compared to the maximum amount the air could hold at that specific temperature, expressed as a percentage.
So 100% means it's holding all it can.
Saturated. Yep, saturated. And crucially, warm air can hold way more water vapor than cold air. So 50% humidity on a hot day is a lot more actual water vapor than 50% humidity on a cold day.
That's why high humidity feels so sticky and hot, right? Sweat doesn't evaporate easily.
Exactly. Evaporation is much slower when the air is already close to holding its maximum moisture.
And then when air cools down to its saturation point, that's the dew point.
That's the dew point temperature, yeah. If air cools to its dew point, condensation happens. On surfaces, you get dew or frost if it's below freezing.
And in the air itself. If rising air cools adiabatically to its dew point,
Then you get clouds. Water vapor condenses onto those tiny aerosol particles, the condensation nuclei, forming billions of tiny water droplets or ice crystals,
and releasing latent heat as it condenses.
which adds buoyancy and can help the cloud grow taller, fueling storms sometimes. It's all connected.
It really is. Okay, let's peel back the layers of the atmosphere itself. How is it structured vertically?
The main way we divide it is by temperature profile, how temperature changes as you go up.
Starting from the ground up.
Right. First layer is the troposphere. That's where we live. Goes from the surface up to maybe 5 to 18 kilometers, lower at the poles, higher at the equator.
And temperature?
Decreases with height. Average 15 degrees C at the surface, down to maybe negative 55 degrees C at the top, the tropopause.
And that temperature drop is key, right? Because it's heated from below.
Exactly. Warm air near the surface wants to rise. Cold air higher up wants to sink. That drives convection, mixing. Tropos means turn or mix in Greek.
So all the weather happens here. Clouds, rain, wind.
Pretty much all of it, yeah. It's the dynamic churning weather layer because of that vertical mixing and because it holds most of the atmosphere's water vapor.
Okay, above the troposphere, past the tropopause.
You hit the stratosphere, goes up to about 50 kilometers, the stratopause. And here the temperature trend reverses.
It gets warmer as you go higher.
Yes, from about negative 55 degrees C at the bottom to near freezing, 0 degrees C at the top.
Why warmer?
Ozone. The ozone layer sits mostly within the stratosphere, and it absorbs incoming UV radiation from the sun. That absorption process heats this layer.
So it's heated from above, making it stable, not much mixing.
Very stable. Stratified, hence the name. That's why planes like flying their smooth air, and why pollutants that get up there can stick around for a long time.
Right, above the stratosphere.
Next up is the mesosphere. Goes from about 50 kilometers up to maybe 85 kilometers, and temperature drops again, quite sharply.
Colder again, why?
It's further away from the ozone heating source, so it just cools with altitude. Gets incredibly cold at the top. The mesopause, maybe 90 degrees, so coldest part of the atmosphere.
And that's where meteors burn up.
Yep. Most shooting stars you see are bits of space debris burning up due to friction as they hit the air molecules in the mesosphere.
Okay, mesosphere.
Then you enter the thermosphere, extends way up, maybe 600 kilometers or more. And here, temperature skyrockets again.
It's hot again. Hundreds, thousands of degrees.
Potentially, yeah. Because the few gas molecules that are up there are mostly nitrogen and oxygen, still absorb really high energy solar radiation like X-rays and short UV. That makes the individual molecules move incredibly fast, which is high temperature.
But it wouldn't feel hot.
Right, because the air is so incredibly thin, practically a vacuum, there are hardly any molecules to actually transfer that heat to you. High temperature, but very low heat content.
Weird concept. And the very outer edge.
That's the exosphere. Basically, the gradual fade into space starts around 600, 700 kilometers. Air is so thin that atoms and molecules can just drift off into space if they're moving fast enough. No clear upper boundary.
Okay, so those layers are based on temperature, but there's another way to divide it based on composition. Homosphere and heterosphere.
Yeah, simpler distinction. The homosphere is the lower part, troposphere, stratosphere, mesosphere, up to about 800 kilometers.
Homo, meaning same.
Right, because turbulence and mixing keep the main gases, nitrogen, oxygen, argon, pretty evenly mixed in the same proportions throughout this region.
And the heterosphere.
That's above the homosphere, basically the thermosphere and exosphere. Hetero, meaning different. Up there, the air is so thin that mixing stops.
So gravity takes over.
Exactly. Gases start to settle out according to their weight. Heavier gases like nitrogen and oxygen are lower down. Lighter ones like helium and hydrogen dominate higher up, stratified by weight.
Makes sense. Then there's the ionosphere. That overlaps these layers, doesn't it?
It does. It's not defined by temperature or overall composition, but by electrical charge. It's a region, mostly in the thermosphere, but dipping into the mesosphere, maybe 60 to 500 kilometers up, where solar radiation is energetic enough to knock electrons off gas molecules.
Creating ions. Charged particles.
Yep, positive ions and free electrons. This electrically charged region is what reflects certain radio waves, allowing long-distance communication.
And it's where the auroras happen. Northern and southern lights.
Exactly. Charged particles from the sun, like from solar flares, get channeled by Earth's magnetic field towards the poles when they hit the atoms and ions in the ionosphere.
They excite them, making them glow.
Precisely. Different gases glow, different colors. Oxygen, often green or red, nitrogen blue or purple. A beautiful display of space weather interacting with our upper atmosphere.
Amazing. Okay, last bit on structure. Pressure and density. They decrease as you go up, right?
Exponentially, yeah. Pressure is just the weight of the air above you. Go higher, less air above, less weight, less pressure. Density is how packed the molecules are. Air is compressible, so the weight of the air above squeezes the air below, making it denser near the surface.
And it drops off fast.
Really fast. Half the atmosphere's entire mass is below about 5.6 kilometers, roughly 3.5 miles up. 90% is below 16 kilometers, about 10 miles. By 100 kilometers, you're above 99.999997% of it.
It really is just a thin skin on the planet.
Incredibly thin, relatively speaking.
Okay, structure covered. Now, how does this thin skin move? Wind and global circulation. What makes wind blow in the first place?
Fundamentally, differences in air pressure. Air always wants to move from an area of higher pressure to an area of lower pressure.
Trying to even things out.
Exactly. The bigger the pressure difference over a certain distance, the pressure gradient, the faster the air moves, the stronger the wind.
And those lines on weather maps, isobars, they show pressure.
Yep. Isobars connect points of equal pressure, like contour lines on a topographic map show elevation. Where isobars are packed close together, the pressure gradient is steep and winds will be strong. Where they're far apart, gentle gradient, light winds.
But the wind doesn't just blow straight from high to low pressure, does it? The Earth's spinning messes things up. Coriolis effect.
Ah, yes, our old friend Coriolis. Because the Earth rotates, anything moving long distances over its surface gets deflected. To the right in the northern hemisphere, to the left in the southern hemisphere.
So the wind starts moving towards low pressure, but gets curved.
Right. High up, away from surface friction, the wind often ends up blowing almost parallel to the isobars, a balance between the pressure gradient pushing it one way and Coriolis deflecting it the other. Near the surface, friction slows the wind down. Coriolis is weaker, so the wind angles across the isobars towards low pressure.
It's complicated.
It adds a twist, literally.
So how does this drive the big global patterns? Why do we have trade winds and westerlies?
That comes down to uneven heating from the sun. The equator gets more direct sunlight, it's hotter. The poles get sunlight at a low angle, it's colder.
Big temperature difference, equator to pole.
That's the engine. Hot air at the equator is less dense, it rises, creating a zone of low pressure there. Cold air at the poles is dense, it sinks, creating high pressure. Air wants to move from the poles towards the equator at the surface and from the equator towards the poles higher up to try and balance the heat.
But Coriolis deflects that movement.
And that sets up large-scale circulation cells. The most distinct are the Hadley cells.
How do they work?
Okay, warm, moist air rises strongly at the equator. That's the intertropical convergence zone, or ITCZ. Lots of clouds and rain there.
The doldrums, where sailing ships got stuck.
Often associated with it, yeah, because the surface winds can be light as the air is mostly going up. This rising air flows towards the poles high up, cools, and sinks around 30 degrees latitude, north and south.
Creating high pressure there.
Yep, the subtropical highs. Sinking air is dry, which is why many deserts are around 30 degrees latitude. Then, at the surface, that sinking air flows back towards the equator.
And gets deflected by Coriolis.
Right. Deflected to the west, becoming the northeast trade winds in the northern hemisphere and southeast trades in the southern hemisphere. That whole loop rising at equator, sinking at 30 degrees, surface flow back, that's the Hadley cell.
A giant atmospheric conveyor belt in the tropics.
Pretty much. Then there's a simplified three-cell model that adds Ferrel cells in the mid-latitudes and polar cells near the poles.
How do they fit in?
The polar cells are similar. Cold air sinks at the pole, flows towards about 60 degrees latitude at the surface, deflected west as polar easterlies, rises there at the polar front, and flows back poleward aloft. The Ferrel cell is kind of like a gear between the Hadley and polar cells driven by them. Its surface winds are generally westerly, blowing west to east.
That three-cell model sounds neat, but the chapter says reality is messier.
Oh, yeah. The Hadley cells are pretty robust, but the Ferrel and polar cells are more like statistical averages. Mid-latitude weather is dominated by migrating high and low pressure systems, big eddies, and a wavy polar front, not a simple fixed cell. Land masses and mountains complicate things too.
Highs and lows, the things that bring our daily weather changes. High pressure, clockwise spin, northern hemisphere, fair weather.
Generally, yeah. Sinking air suppresses clouds.
Low pressure, counterclockwise, rising air, clouds, storms.
That's the typical association. These systems drift along, steered by winds higher up.
Speaking of winds higher up, jet streams. What are those? Rivers of air.
That's a great way to think of them. They're narrow bands of very strong winds, mostly westerly, blowing near the top of the troposphere around the tropopause level.
Why are they there? And why so fast?
They form at the boundaries between large air masses with big temperature differences, like between cold polar air and warmer mid-latitude air. This temperature contrast creates a sharp pressure gradient aloft, and Coriolis cranks up the wind speed parallel to the boundary.
So fast winds high up because of temperature differences down below. There are two main ones, polar and subtropical.
Yeah. The polar jet stream is usually stronger, lower down, maybe 7-12 kilometers, and associated with the polar front. It's often quite wavy. The subtropical jet is higher, 10-16 kilometers, generally weaker, and near the boundary of the Hadley cell.
And these waves in the jet stream steer the surface highs and lows.
They play a huge role. Where the jet stream bends or changes speed can help create or intensify surface pressure systems. And pilots know all about them. Catch a tailwind in the jet stream flying east, you save a lot of time and fuel. Fly west against it, it's a struggle.
Right. Okay, that's the big picture movement. Let's zoom into weather. What's the difference between weather and climate again? People mix them up.
Easy to do. Weather is what's happening now or in the very near future. Temperature, rain, wind, clouds, today, tomorrow. It's the atmosphere's condition at a specific time and place. Exactly. Climate is the long-term picture. It's the average weather conditions for a region based on decades of data, usually 30 years. It includes the averages, the typical variability, the extremes, the overall pattern.
The movie, not the snapshot. Got it. Now, weather often changes when different air masses move in. What defines an air mass?
An air mass is just a huge chunk of air, hundreds or thousands of kilometers across, that has pretty uniform temperature and humidity.
Where do they get those characteristics?
They form when air sits over a large uniform area, the source region, for a while, taking on its properties. Air sitting over cold, snowy Canada in winter becomes a continental polar CP air mass, cold and dry. Air over the warm Gulf of Mexico becomes maritime tropical, MT, warm and humid.
And when these move, they bring that weather with them.
Yep. A CP air mass moving south brings a cold snap. An MT air mass moving north brings warm, muggy conditions.
And when different air masses meet, that's a front, like on the weather map.
Exactly. A front is just the boundary zone between two different air masses. Because they have different densities, cold air is denser than warm air, they don't mix easily.
So weather happens at the boundary.
Often the most active weather. Take a cold front. Cold, dense air is actively pushing under warmer, lighter air. It forces the warm air up rapidly.
Steep slope, fast lifting.
Right. That leads to rapid cooling, condensation, often tall cumulonimbus clouds, heavy showers, maybe thunderstorms, gusty winds. They usually move pretty fast.
Okay, and a warm front.
That's where warm air is advancing and gently gliding up and over retreating colder air. The slope is much gentler.
So slower, more widespread lifting.
Yep. Leads to a sequence of clouds forming ahead of it, high cirrus first, then mid-level altostratus, then lower stratus. Precipitation is usually lighter, steadier, and more widespread drizzle or light rain.
And sometimes fronts get tangled up, occluded fronts.
That happens when a faster cold front catches up to a slower warm front. It lifts the warm air completely off the ground, sandwiched between cold air behind and cool air ahead, or vice versa. Weather can be complex, often widespread cloud and precipitation, marking the mature stage of a low-pressure system.
So these fronts are key parts of those big low-pressure systems, the mid-latitude cyclones.
Absolutely integral. A typical mid-latitude cyclone starts as a wave on a stationary front, then develops distinct cold and warm fronts rotating around a low-pressure center, counterclockwise in the northern hemisphere.
And these cyclones bring the storms.
They're often associated with clouds, precipitation, strong winds, what we typically call stormy weather. They draw contrasting air masses together, creating the fronts where lifting occurs. High-pressure systems, or anticyclones, are the opposite, sinking air, rotating clockwise, usually bringing clear skies and fair weather.
Lows are lousy, highs are happy. A bit simplistic, but...
A useful starting point. These systems are steered by the jet stream, developing, maturing, occluding, and eventually dying out as they move across the landscape.
Okay. Let's talk clouds and rain specifically. We know rising, cooling, moist air makes clouds. But how do tiny cloud droplets become big enough to fall?
Right. Cloud droplets are minuscule. They need to grow much, much larger to become precipitation. There are two main ways.
Okay.
In warmer clouds, ones entirely above freezing, it's the collision coalescence process. Droplets drift around, bump into each other, and merge, coalesce. Bigger drops fall faster, collecting more small ones. Eventually, they get heavy enough to fall as rain.
Simple bumping and sticking. What about colder clouds with ice?
That's where the Bergeron process, or ice crystal process, comes in. This happens in clouds cold enough to have both ice crystals and supercooled water droplets, liquid water below freezing.
And supercooled water, how does that work?
Water needs a nucleus to freeze onto, just like it needs one to condense onto. Without ice nuclei, water can stay liquid well below 0 degrees C.
Okay, so you have ice crystals and supercooled droplets together.
Here's the key. Water molecules evaporate more easily from the supercooled droplets than they do from the ice crystals, so water vapor moves from the droplets to the ice crystals.
The ice crystals grow by stealing water from the droplets.
Essentially, yes. The ice crystals grow rapidly at the expense of the evaporating droplets. They get heavy, start to fall.
And they reach the ground as?
Depends on the air below the cloud. If it stays freezing all the way down, they fall as snow. If they fall through a warm layer, they melt into rain. If they melt, then fall through a freezing layer near the ground, they refreeze as sleet.
Got it. Different paths to precipitation. Now, storms. Nature's fury, as the chapter says. What makes something a storm?
Generally, strong winds, heavy precipitation, rain, snow, hail, maybe lightning and thunder, usually linked to strong pressure gradients and unstable air that allows rapid vertical cloud growth.
Thunderstorms seem like the classic example. What kicks them off?
You need three basic things: moisture, warm, humid air near the ground, instability, air that keeps rising once it starts, and a lifting mechanism, like surface heating, a front, or mountains, to get it going.
Warm, moist air gets lifted, cools, condenses, releases latent heat.
Making it even more buoyant so it rises faster. That creates the strong updrafts in a cumulonimbus cloud, the thunderhead.
And there are basic ones and nasty ones.
Yeah.
Ordinary versus supercell.
Yeah. Ordinary thunderstorms are common, relatively short-lived. They have an updraft, then develop a downdraft as rain falls, and that downdraft eventually chokes off the updraft, killing the storm. Develop, mature, dissipate.
Okay. Supercells.
They're different beasts, much more organized, much longer lasting, often severe. The key is rotation. They have a rotating updraft, a mesocyclone.
How does it start rotating?
Usually wind shear, wind changing speed or direction with height. This creates horizontal rolls of air like tubes. The thunderstorm's strong updraft can then tilt one of these tubes vertically, creating the mesocyclone.
And that rotation keeps it alive longer.
Yes, it helps separate the main updraft from the downdraft and precipitation area, so the storm doesn't choke itself off. It can keep regenerating for hours, producing large hail, damaging winds, and often tornadoes.
Hail. How do those ice chunks form?
Inside the powerful updrafts of thunderstorms, especially supercells, raindrops get carried way up into the freezing parts of the cloud. They freeze, becoming little ice pellets.
And then,
The updraft keeps tossing them up and down. On the way up, they collect supercooled water, which freezes onto them in layers like an onion. Stronger updraft means they stay up longer, make more trips, collect more ice, get bigger.
until they're too heavy for the updraft.
Exactly. Then they fall out. Can range from pea size to grapefruit size in extreme cases. Destructive stuff.
And lightning, the electrical part.
That's all about charge separation in the cloud. Collisions between ice crystals, supercooled water, and hail inside the turbulent cloud strip electrons separating charges. Typically, the top of the cloud becomes positive, the bottom negative.
Like a giant battery.
Pretty much. When the charge difference gets big enough between parts of the cloud, or between the cloud base and the ground, the air can't insulate anymore, boom. Lightning. A massive electrical discharge.
And thunder is just the sound of that.
It's the sound of the air along the lightning channel being heated instantaneously to temperatures hotter than the sun's surface. It expands explosively, creating a shock wave. That shock wave is the thunder we hear. Light travels faster than sound, so flash, then bang.
Count the seconds. Okay, the scariest storm phenomenon. Tornadoes. What are they?
A tornado is a violently rotating column of air touching the ground, extending down from a cumulonimbus cloud, almost always a supercell.
How do they form from the supercell's rotation?
It's complex, but often involves the mesocyclone aloft and interactions with downdrafts near the ground.
But
A downdraft can bring rotation down towards the surface, and then the updraft can stretch that column of rotating air vertically, making it narrower and spin much, much faster, like a figure skater pulling their arms in.
conservation of angular momentum.
Exactly. Creates an intense low-pressure vortex with incredibly destructive winds. Rated on the enhanced Fujita EF scale based on damage. Most common in places like the U.S. Tornado Alley where contrasting air masses frequently collide.
Terrifying power. What about bigger storms? Nor'easters.
Nor'easters are just intense mid-latitude cyclones that track up the east coast of North America, especially in winter. They get their name because the winds hitting the coast often come from the northeast as the storm spins counterclockwise.
Known for big snowstorms. Blizzards.
Yep, heavy snow, strong winds, coastal flooding from high waves, and storm surge. They can be massive and very disruptive. They're fundamentally the same type of storm system as the lows that cross the rest of the country, just often intensified by the contrast between cold land and the warm Gulf Stream offshore.
Okay, finally the biggest storms of all.
Mm-hmm.
Hurricanes, or typhoons, or tropical cyclones.
Right, different names, same phenomenon. These are huge rotating storms that form over warm tropical oceans.
What's the key ingredient?
Warm ocean water needs to be at least 26.5 degrees C, about 80 degrees out, down to a decent depth. That warm water provides the fuel.
How? Evaporation.
Massive evaporation. The warm, moist air rises, cools, condenses into towering thunderstorms, releasing enormous amounts of latent heat. That heat release warms the core of the storm, lowers the pressure further, drawing in more moist air from the surface. It's a powerful, positive feedback loop.
A heat engine fueled by warm water. What else do they need?
Low wind shear is important, meaning the winds don't change much with height, allows the storm to grow vertically without being torn apart, and they need to be away from the equator, usually at least 5 degrees latitude, so the Coriolis effect is strong enough to get them spinning.
And they grow in stages. Disturbance, depression, storm, then hurricane.
Right. Tropical disturbance is just a cluster of thunderstorms. If it gets organized with circulation, it's a depression. Once winds reach 39 mile-per-hour, 63 kph, it's a tropical storm and gets a name. At 74 mile-per-hour, 119 kph, it's officially a hurricane or typhoon cyclone.
And that structure, the eye in the middle.
Yep.
The eye is the calm center, sinking air, light winds. Surrounded by the eye wall, a ring of the most intense thunderstorms, strongest winds, heaviest rain. Then spiral rain bands extend outwards. Air spirals in at the bottom, up violently in the eye wall in bands, and out at the top.
And they die out over land or cold water.
Yeah, cut off from their warm water fuel source, they weaken. Friction over land also helps slow them down.
Damage comes from wind, rain, and storm surge, right? What's storm surge?
It's often the deadliest part. It's an abnormal rise in sea level pushed ashore by the storm's winds, plus a smaller effect from the low pressure. Imagine the wind piling up water against the coast. It can flood huge areas, meters deep. Combine that with high tide and waves, it's devastating.
Like with Katrina in New Orleans.
Katrina was a tragic example of catastrophic storm surge overwhelming flood defenses. Sandy showed how surge can impact even non-tropical areas when a hurricane interacts with other systems. Haiyan in the Philippines had some of the strongest winds ever recorded and an absolutely devastating surge. They are incredibly powerful systems. Sobering stuff. Okay, we've weathered the storms. Last stop. Global climate. We know weather versus climate, but what controls the long-term climate of a place?
It's a combination of factors. Latitude is number one, how much solar energy you get, the seasonality.
Equator hot, poles cold, mid-latitude seasonal.
Basically, elevation is huge. Higher up is colder, even at the equator. Think mountain glaciers.
Huh?
Proximity to water. Oceans' moderate temperature coasts have smaller temperature swings than deep inland areas. Water heats and cools slowly.
Continental versus maritime climates.
Exactly. Ocean currents matter too. The Gulf Stream keeps Western Europe milder than Labrador at the same latitude. Cold currents cool adjacent coasts.
Like California current.
Right. Mountains act as barriers or a graphic effect. Windward side gets rain as air is forced up. Leeward side is in a dry rain shadow.
Position in those global circulation cells we talked about, ITCZ versus subtropical highs.
Big influence. ITCZ regions are generally wet. Subtropical high regions around 30 degrees are generally dry deserts. And the dominant air masses affecting a region contribute too.
So it's a mix of geography and atmospheric patterns. How do scientists classify all these different climates?
There are various systems. The most common is Köppen classification. It uses average monthly annual temperature and precipitation data.
And vegetation often reflects the climate type.
Very strongly. Different plants thrive in different temperature and moisture regimes. Köppen has broad categories like tropical, arid, dry, temperate, cold, and polar, with many subcategories based on rainfall seasonality and temperature details.
And climate isn't perfectly static, right? There's variability like monsoons, El Niño.
Definitely. Climate includes natural variability. Monsoons are huge seasonal wind shifts causing distinct wet-dry seasons, especially in Asia. El Niño is a multi-year fluctuation in Pacific Ocean temperatures and atmospheric pressure that affects weather worldwide. These are natural cycles within the broader climate system.
Wow. Okay, that was a journey. From the first wisps of hydrogen to supercell thunderstorms and the whole global climate system. We covered a lot from that chapter.
We really did. Hopefully you listening have a clearer sense now of how the atmosphere formed, its layers, how air moves, what causes our weather from gentle breezes to furious storms, and the factors shaping climate zones across the planet.
Yeah, connecting the dots between, say, adiabatic cooling and cloud formation, or the Coriolis effect and hurricane rotation,
Yeah.
getting those aha moments.
It's a complex system, but hopefully less intimidating now. From the tiny aerosols to the giant jet streams, it all fits together.
So a final thought to leave everyone with.
Well, think about how sensitive the whole Earth system is to atmospheric composition. The rise of oxygen transformed the planet. The current increase in greenhouse gases is driving major changes now. What other, maybe more subtle atmospheric changes or processes might hold surprising power to shape our future world? Something to ponder.